Before we understand snapshot isolation, we need to understand why it was invented. And to understand that, we need to understand what happens without it. Read committed is the weakest isolation level that most databases consider acceptable. Oracle 11g, PostgreSQL, SQL Server, and MEM-SQL all default to it. It promises two things: you only read data that has been committed, no dirty reads, and you only overwrite data that has been committed, no dirty writes. Dirty reads are easier to visualize. Transaction A updates a row but hasn't committed yet. Transaction B reads that row and sees the uncommitted value. Now transaction A aborts. Transaction B made a decision based on data that technically never existed. In financial systems, this can mean a user sees a balance transfer in progress and acts on it, then the transfer is rolled back. The user has made an irreversible external action based on a lie. Dirty writes are more subtle. Transaction A updates row 1. Before A commits, transaction B updates row 1 again. Now A commits, but it overwrites B's write, which happened after A's write. B's change is lost even though B committed after A. Read committed prevents both. The usual implementation doesn't use read locks that would block reads whenever anything is being written, which would be terrible for performance. Instead, the database stores the old committed value alongside the new in-progress write. Reads always return the most recently committed value. Writers only block other writers. This solves dirty reads and dirty writes. But read committed still allows read skew, a more subtle problem that requires snapshot isolation to fix. Alice has 2 bank accounts, each with 00. Total, 000. A bank transfer moves 00 from account 1 to account 2. Alice reads account 1 at the start of the transfer, she sees 00 before the 00 debit. She reads account 2 at the end of the transfer, she sees 00 after the 00 credit. Alice's total, 100. She just saw 00 that doesn't exist. No dirty reads occurred. She only read committed data. But she saw the database in a state that never actually existed as a single consistent snapshot. She saw account 1 before the transfer and account 2 after it. This is called read skew, or a non-repeatable read. For Alice checking her balance, it's confusing but not catastrophic. For backup operations reading a dataset that must be consistent, it's a serious problem. The backup captures a mix of before and after states. For analytics queries joining multiple tables, a read skew can cause aggregations to be wildly incorrect. Snapshot isolation fixes this by giving each transaction a consistent snapshot of the database as it appeared at the moment the transaction started. Alice's transaction started before the transfer. She sees account 1 as it was before the transfer, and account 2 as it was before the transfer. Her total is 000, correct. The key insight: when a transaction reads any row, it sees the version of that row that was committed before this transaction started, not whatever the latest committed state is at the moment of the read. The snapshot is frozen at transaction start time. Snapshot isolation is the default in PostgreSQL, MySQL InnoDB, Oracle, called serializable in Oracle's documentation, confusingly, and SQL Server. It's one of the most important correctness features a database can offer. Snapshot isolation requires the database to maintain multiple versions of the same row simultaneously, one for each transaction that is written to it. This technique is called multi-version concurrency control, or MVCC. Here's the mechanics. Every row in the database gets 2 metadata fields, created_by, the transaction ID that inserted this version of the row, and deleted_by, the transaction ID that deleted it, initially null. When a transaction updates a row, it doesn't overwrite the existing row, it creates a new version with the current transaction ID and created_by, and marks the old version with the current transaction ID and deleted_by. When a transaction reads a row, it only sees versions where created_by is a committed transaction that started before the current transaction, and deleted_by is either null or a transaction that started after the current transaction. Everything else is invisible. The result: readers never block writers. A read transaction never has to wait for an in-progress write to finish, because it's looking at an older version. Writers never block readers for the same reason. A write creates a new version, reads go to the old version. The book emphasizes that this property, reads never blocking writes, writes never blocking reads, is the primary performance advantage of MVCC over lock-based approaches. The cost is storage. Old versions of rows accumulate. PostgreSQL runs a background process called vacuum that periodically removes versions that are no longer visible to any active transaction. If vacuum can't keep up, because transactions run too long or vacuum is misconfigured, the database accumulates table bloat, gigabytes of dead row versions that make storage and scans progressively slower. MVCC turns the isolation problem from a locking problem into a versioning problem. That trade-off, storage and cleanup complexity in exchange for concurrency, is one of the most important design decisions in modern database engineering.